Hello, everyone. In this video, we're going to look at example 2 in section 6.4. All right, so in example 2, we're told that a 45-meter rope with a mass of 30 kilograms is dangling over the edge of a cliff. Ignoring friction, how much work is needed to pull the rope up to the top of the cliff? So let's go ahead and start by just drawing an example of what's going on. All right, so here's our cliff. It's a scary looking cliff. And we have a rope here dangling from the end of it. So here's our rope. Okay, and what other information are we told? Well, we're told that this entire rope has a length of 45 meters and a mass of 30 kilograms. Okay, and we're going to try to compute work needed to pull the rope up to the top of the cliff. Let me label here so it's obvious, cliff. Okay. So part A asks us to explain what is wrong with the following solution in the above problem. So here we're given a possible solution, but we're told it's wrong and we need to figure out why. Okay, so we're starting to compute work. Work they have as force times distance. So far, that looks correct. So distance being 45 meters, force being 294 newtons. So let's go ahead and check that. So how might we compute the force on this rope? Well, for us, we're told that the mass of the rope is 30 kilograms. And then we know the force due to gravity on the rope is 9.8 meters per second squared. So we can take a look. Have they computed the weight here? 30 kilograms times 9.8 meters per second squared. Is that our force? And we see that when we multiply that together, indeed, we do get the 294 newtons. So that checks out. And then our distance is 45 meters. And we multiply those together, check, we do get 13,230 joules. So what's wrong with this solution? I encourage you to take a moment to pause the video and think through the solution and why it is not correct. Okay, well, let's think about it on a more smaller scale. So we want to drop or pick up this entire rope and move it to the top of the cliff. So what we can see here is that, yes, a point all the way down at the bottom of the rope, that needs to move the entire 45 meters. But what about a part of the rope that's like in the middle? Does it have to move an entire 45 meters up? No, it doesn't. It only has to move halfway up. So the problem is that not every part of the rope is going to move 45 meters. So let's go ahead and write that down. So the problem is that not every part of the rope moves 45 meters. If we were to pick this rope straight up for 45 meters, then yes, this is how we would compute the work. But we're not going to do that. We're just going to pull up the rope to the top of the cliff, not 45 meters above the cliff. All right, so let's think about how we should actually solve this problem. We have the opportunity to do so in part B, where it says give a correct solution to this problem. So I redrew our picture here just so we have a place that we can work from. Okay, so let's think about how we should correctly solve this problem. So keeping in mind that each piece of the rope is going to move a different length up, we should think about this problem by cutting up our rope into pieces. So think little slices, just like we did a similar method that we did to compute area or volume under a curve. We chop it up into little pieces. So here we're computing total work. So we chop up this rope into little pieces and see if we can determine the work done on each piece. I'm going to take a piece here and I'll call it a slice because that's the language we've been using. So the goal here, or maybe the first goal, is to compute the work needed to move a slice to the top of the cliff. Okay, so let's just go through how we're going to compute that work. So let's recall, what is work? So work is equal to force times distance. So the force we're going to compute is the weight, which is mass times that acceleration of gravity times distance. So let's take it one step earlier and first then compute the weight of a slice. Weight of slice. So we need to include all these components, weight and distance of slice, but first we need to break down each component. So first computing the weight of a slice. So how do we compute weight? Well, weight is going to be mass times acceleration of gravity. Because we are assuming we're on the surface of Earth. So mass, are we told anything about the mass of a slice? No, we're just told information about the mass of the entire rope. So how are we going to determine the mass of just a slice? Well, to do that, we need to figure out the density of the rope. So let's go ahead and do that first. So we're told that the entire rope, you can highlight it here, the entire rope is 30 kilograms, and the entire length of the rope is 45 meters. So backing up here, we can compute the density of the rope. Density is going to be equal to 30 kilograms per 45 meters. So this is a one-dimensional object. A rope is one-dimensional. So the density is our mass per unit length. So for us, that would be this 30 over 45 kilogram per meter. So then to compute the mass of a slice, this slice here, we need to figure out, or we have rather, the density, but we need to multiply that density by the length of the rope. And in this case, we're still looking at slice, a slice of the rope. So a slice here is just a little delta y, or I could say dy. So the length of a slice is dy. Okay, so let's put these two things together to determine the mass of the rope. And I keep saying rope, but I mean slice. We're looking at just a slice here. So then mass of slice, as we saw in the last section, is density times length. And we computed those. So it'd be 30 over 45 times dy, and that would be kilograms per meters. So here is our mass of a slice. All right, so we're almost done computing the weight of a slice. That's what we're focusing on here. Okay, so then what would the weight of a slice be? Again, that would be mass times acceleration due to gravity. So we found the mass to be 30 over 45 dy's. And the acceleration due to gravity is the constant 9.8 meters per second squared. So if we multiply those two together, we get 294 over 45. And then what will our units be? So here in mass, we have kilograms per meter times meter, because we multiplied by length. So those two cancel out. Acceleration due to gravity is meter per second squared. So here we get for units, can erase the units associated with just the gravity. And the total units here would be kilograms, meters per second squared, which, as we saw, is the same thing as newtons. Okay, so what we just computed was the weight of a slice. Beautiful. Okay, so our ultimate goal is to figure out the work needed to move a slice to the top of the cliff. So just to recap, how we need to compute, or how we compute work, is to compute force times distance. To compute force, we computed the weight of the slice. The weight of the slice is going to be the mass times acceleration due to gravity. To compute mass, we had to compute density of the entire rope multiplied by the little length of that slice. In total, we got a mass of 30 over 45 dy, kilograms per meter. And notice I made a small typo here. This should just be kilograms because we multiplied dy is meters. 30 over 45 is kilogram per meter. So those meters cancel out. So we're just with kilograms here. We saw that when we looked at units down here, but just wanted to make sure that's clear for your notes. Okay, so then filling in those two bits of information, the mass and then the acceleration due to gravity, we computed the entire weight of a slice. Okay, so then to determine the work of a slice, again, which was our original hope, we need to compute, so work, the force times distance. So we know the force to be 294.45 dy, and those are newtons. And the distance that our slice will travel, we have to put some orientation here. So let's say that this vertical rope, we could think about that as like a y-axis. So we can think, okay, a slice down here, how far does it have to travel? We can call it y. So we can call y the length that the rope has to travel, that the slice rather has to travel. I won't say length, I'll say distance. Distance slice travels. Okay, so now what we've just computed is the work needed to move one slice located y meters below the cliff to the top of the cliff. So I encourage you at this point in the video to pause and just go over the notes that you took. Make sure you're following with the steps that we've taken so far. And then also think about what our next step would be to compute the work needed to move the entire rope to the top of the cliff. All right, and when you're ready, let's take a look together. So now we're going to compute. I'm going to just add another page here. Now we're going to look at the work needed to move the entire rope to top of cliff. Well, what we just did was determine the work for a slice. Work to move a slice. So we need to add up the work required to move all of the slices of our rope to the top. So what tool can we use to do that? Well, we can use an integral. So awesome idea here is we can add up work to move all slices to top of cliff using an integral. All right, so then we're going to add up using this integral the work to move all of our slices. So we have 294 over 45. And I'm going to put the y first, just because typically conventionally we put the dy at the end. So then what would our bounds here be on our integral? So we want to ask the question, well, what are the values of y? What do they range from? Well, the smallest value of y is right at the top, where the slice is already at the top. So the y that it has to move is 0. Then the furthest that a slice would have to travel is a slice down here at the end of the rope. And the length that that piece or slice has to travel is the whole 45 meters. So then our bounds here would be from 0 to 45. Awesome. So let's go ahead and compute this integral. We are on the home stretch now. So let's first observe that this 294 over 45 is a constant. So we can go ahead and bring it out, 294 over 45. You have the integral from 0 to 45, y dy. So now we can find the antiderivative there. Still have our constant, 294 over 45. So the antiderivative is just going to be y squared over 2, keeping in mind that power. Then we're going to evaluate at 45 and 0. So that becomes 294 over 45 times 45 squared over 2 minus 0. 0 squared over 2 is just going to be 0. When we do that final calculation, we're going to get 6,615. And checking units, our work was newtons, our distance was meters. And recall that dy is with the n, but we're just talking about units here. So in final, our units will be joules. And now we've found the correct solution to our original question. Awesome, great work going through this example.